Somewhere in the astronomical archives there's a photograph of an object that could sterilize Earth, and for 7 years it was labelled minor planet, not a threat. Bernardinelli-Bernstein, a comet the size of Florida, 1,000 times more massive than anything we're currently tracking in the inner solar system, and 5 times wider than what ended the age of dinosaurs. Astronomers saw it clearly. They just didn't understand what they were seeing. No tail, no coma, just a solid point of light that looked exactly like a harmless chunk of ice drifting through deep space. And here's the thought that should whisper at the edge of your consciousness tonight. How did we miss this? A comet that, if aimed at Earth, would render every deflection strategy we've ever conceived completely irrelevant. Stay until the end and discover how the king of comets exposed the most dangerous assumption in astronomy, that we'd see it coming. If this cosmic filing error has you questioning what else we've missed, hit like and subscribe so you're here when we explore the other threats lurking in archival data. Leave a comment telling us where you're tuning in from, what time zone you're in, and whether you think planetary defense is ready for what the Oort Cloud might throw at us next, or if we're still flying blind. Part 1. The mistake that only happens once per century. Somewhere in the cosmic filing cabinet of human discovery, there exists a mistake so enormous that when astronomers finally realised what they'd done, the correction changed everything we thought we knew about the outer limits of our solar system. This wasn't a typo, this wasn't a rounding error, this was a misidentification so fundamental that it revealed a dangerous truth about how we categorise the universe. Sometimes the most terrifying objects are the ones we've already seen but failed to recognise. In 2014, cameras pointed at the sky weren't looking for comets. They were hunting for something far stranger, the invisible architecture of the universe itself. The Dark Energy Survey was designed to map how galaxies cluster and how the cosmos expands, documenting the slow warping of space-time across billions of years. But every night, as those cameras stared into the void, they also captured something closer to home, something that shouldn't have been there, something that, at the time, nobody understood was a threat hiding in plain sight. The object appeared as a single point of light, drifting slowly through archived images like a ghost passing through walls. Astronomers call these archival detections, and they come with a peculiar kind of danger. When you discover something in real time, alarm bells ring, telescopes swivel, observers scramble, but when you find something years after it was photographed, there's no urgency, no immediate follow-up, just a dim speck in old data, waiting patiently to be noticed. And that's exactly what happened with Bernardinelli-Bernstein, catalogue designation C/2014 UN 271. At roughly 30 astronomical units from the Sun, about the distance of Neptune, this object should have been screaming its identity. If it were a comet, it should have been glowing, outgassing, trailing a faint haze of sublimating ice. But it wasn't. It appeared clean, solid, planet-like, and that absence of fuzziness, that lack of what astronomers call a coma or tail, made it look exactly like what it wasn't. A dwarf planet drifting through the outer solar system, minding its own business. You have to understand how detection logic works to appreciate the trap astronomers walked into. When you see something bright at 30 AU, you calculate backwards. You measure its brightness, estimate its reflectivity, and solve for size. Dwarf planets are dark, rocky, or icy worlds that reflect very little sunlight. Comets, by contrast, are small but appear bright because they're surrounded by clouds of gas and dust that scatter light in every direction. Bernardinelli-Bernstein was bright, but it had no cloud, so the math led to an inescapable conclusion. This thing had to be huge. The numbers came back terrifying. 120 to 137 kilometers wide, larger than any comet nucleus ever observed, larger than some moons. A frozen behemoth lurking in the archives, and nobody panicked because it was filed under the wrong name. It fit the profile of a distant Kuiper Belt object, or a scattered disk wanderer, not a comet preparing to wake up. The orbital arc made sense, the brightness made sense. Everything made sense except the part that mattered most, what it actually was. Scientific papers have a way of burying the most important revelations under layers of cautious language. Words like notably large and exceptional diameter sound calm, professional, measured. But when you translate that into plain English, what they're really saying is this: we found something that breaks the scale. We found something that doesn't fit. We found something we don't have a category for, and we almost missed it entirely because we thought it was something else. Here's the question that should keep you awake at night. If the largest comet ever discovered was initially mistaken for a minor planet, how many other objects are still sitting in our databases under the wrong classification? How many slow-moving giants are drifting through the outer solar system right now, filed away as harmless debris, waiting for someone to realise they're not harmless at all? The mistake with Bernardinelli-Bernstein only happened because someone decided to look closer, but there's no guarantee that will happen again. And the next misidentified object might not give us years of warning. It might give us months. The scariest part isn't that astronomers made a mistake. The scariest part is that the mistake made perfect sense. The logic was sound. The assumptions were reasonable. And that means we're not just dealing with human error. We're dealing with a systematic blind spot in how we see the cosmos, a flaw in the very framework we use to decide what's dangerous and what's not. Bernardinelli-Bernstein didn't hide. It was right there, glowing in the archives. We just didn't know what we were looking at. Part 2. A point of light the size of a world. Let's talk about brightness, because brightness is where the illusion begins. When you look at the night sky, every star appears as a tiny dot of light. Some are brighter than others, and your brain instinctively assumes the bright ones are bigger or closer. But in astronomy, brightness is a liar. It tells you almost nothing about what you're actually looking at without additional context. A small object close by can appear just as bright as a massive object far away. A dark surface can hide enormous size. And when you're dealing with something 30 astronomical units from the Sun, roughly 2.8 billion miles away, brightness becomes a puzzle with multiple solutions. Bernardinelli-Bernstein was bright. Not dazzling, not obvious, but measurably bright for something so far from the warmth of the Sun, and that brightness created a problem. Astronomers had to solve backwards. How big does an object need to be to appear this bright at this distance? The answer depends entirely on one variable called albedo, which is just a fancy word for reflectivity. How much sunlight does the surface bounce back into space? A shiny ice ball reflects more light than a chunk of charcoal, and that difference changes everything. Typical comet nuclei, the solid frozen cores beneath all that gas and dust, range from 1 to 10 kilometres across. They're dirty snowballs, dark and porous, with albedos hovering around 4 to 6%. That means they absorb 94 to 96% of the sunlight that hits them. They're nearly black. But Bernardinelli-Bernstein wasn't behaving like a typical comet. It had no coma, no tail, no visible outgassing. So astronomers initially assumed it might have a higher albedo, something closer to 10 or 15%, like some Kuiper belt objects. That assumption led to size estimates in the range of 100 kilometres. Large, yes. Unprecedented, absolutely. But still within the realm of icy bodies we thought we understood. Then the refinements began. As more observations poured in, as orbital calculations improved, as spectroscopic data revealed surface composition hints, the albedo estimates dropped. And when albedo drops, size estimates climb. Because if the object is darker than you thought, it has to be bigger to produce the same brightness. The final numbers settled into a range that sounded almost absurd, 120 to 137 kilometres in diameter. For context, that's larger than the distance from Los Angeles to San Diego. That's a mountain range floating in space. That's a frozen world pretending to be a comet. Here's where the Kuiper belt logic trap reveals itself. The Kuiper belt is full of large objects. Pluto lives there. Eris, Makemake, Haumea. These are worlds with diameters measured in hundreds or even thousands of kilometres. So finding something 130 kilometres wide shouldn't be shocking, right? Except Bernardinelli-Bernstein wasn't sitting quietly in the Kuiper belt. It was falling inward. Its orbit was long, elliptical and extreme. It came from somewhere far beyond the Kuiper belt, from a region we barely understand and can't easily observe, and that changed the entire statistical distribution. The Kuiper belt is close enough that we've surveyed it fairly well. We know the size distribution, we know how many large objects there should be and roughly where they should be. But the Oort Cloud, the hypothetical spherical shell of icy debris surrounding the solar system at unimaginable distances, remains mostly theoretical. We've never directly imaged it. We infer its existence from the comets that occasionally fall inward, and those comets are almost universally small, a few kilometres across, maybe 10. The idea that something 130 kilometres wide could be lurking out there, that the Oort Cloud might contain objects this massive, wasn't part of the model. Scientists started running the numbers. How many objects this size could exist in the Oort Cloud without us having seen them before? How rare is Bernardinelli-Bernstein? Is it a statistical outlier, a 1 in a billion fluke? Or is it the first detected member of a population we never knew existed? The math didn't provide comforting answers. If Bernardinelli-Bernstein is truly unique, then we got extraordinarily lucky to spot it in our lifetimes. But if it's not unique, if there are dozens or hundreds of objects this size drifting through the outer solar system, then we've been living under a cosmic sword of Damocles without realizing it. The moment scientists realized they were dealing with something outside the existing size distribution was the moment everything shifted. This wasn't just a large comet. This was an anomaly, a category breaker, something that forced astronomers to rewrite their assumptions about what the outer solar system contains and how much mass might be hiding in the darkness. And the terrifying part, size alone doesn't explain what happened next, because Bernardinelli-Bernstein wasn't done revealing itself. It was just getting started. Part 3, the outgassing that changed everything. For a while, Bernardinelli-Bernstein sat in the catalogues as a dwarf planet candidate, quietly minding its own business. Astronomers tracked it. They refined its orbit. They calculated where it came from and where it was going. And then, in observations taken between 16 and 20 astronomical units from the Sun, something impossible happened. The object started breathing. Outgassing sounds technical, but it's actually one of the simplest processes in the solar system. Imagine a frozen lake in winter. The water is solid, locked in place by cold. But when spring arrives and the sun warms the surface, the ice doesn't just melt. Some of it skips the liquid phase entirely and transforms directly into vapour. That's sublimation. And in space, where pressure is nearly zero, sublimation happens constantly. Water ice, methane ice, carbon dioxide ice. They all sit frozen on the surfaces of distant objects until sunlight provides enough energy to turn them into gas. And when that gas escapes, it creates jets, plumes, activity, the signature of a comet waking up. Carbon monoxide is special. It's what astronomers call a super volatile ice, meaning it doesn't need much heat to sublimate. Water ice requires temperatures above about 200 degrees Kelvin to start outgassing significantly. But carbon monoxide, it starts sublimating at temperatures well below 150 degrees Kelvin. That's cold. That's Neptune distance cold. And that's exactly where Bernardinelli-Bernstein started showing signs of life. The Atacama Large Millimeter Array, or ALMA, is a collection of radio telescopes in Chile designed to detect faint emissions from cold gas in space. When astronomers pointed ALMA at Bernardinelli-Bernstein, they weren't sure what they'd find. But what came back was unmistakable. Carbon monoxide, lots of it, streaming off the surface in localized jets, concentrated in specific regions rather than spread evenly across the nucleus. This wasn't a gentle diffuse leak. This was pressurized outgassing, the kind that happens when subsurface ice heats up, builds pressure, and then bursts through weak spots in the crust. Here's what didn't happen. Bernardinelli-Bernstein didn't suddenly sprout a massive glowing tail. It didn't transform into the classic image of a comet with a streaming banner of gas and dust stretching millions of miles behind it. At 16 to 20 AU, it was still too far from the Sun for that kind of dramatic activity. What it did instead was reveal its true nature in a subtle way. Those jets, those localized vents of carbon monoxide, were the smoking gun. This was no dwarf planet. This was a comet unlike anything we'd ever seen before. The absence of a visible coma makes sense when you understand the physics. A coma forms when outgassing becomes intense enough that the escaping gas and dust create a cloud around the nucleus, scattering sunlight and making the comet appear fuzzy. But Bernardinelli-Bernstein is so massive that its gravity pulls some of that gas back down. The outgassing is real, but it's not strong enough yet to overcome the object's own gravitational field and create a persistent atmosphere. It's like watching a volcano emit steam without seeing the full eruption. The activity is there, you just have to look for it in the right wavelength. Why does this matter? Because those jets revealed something profound about what Bernardinelli-Bernstein actually is. Comets that have made multiple passes through the inner solar system tend to develop thick, dusty crusts. The surface ice sublimates away, leaving behind a layer of non-volatile material that insulates the interior. But Bernardinelli-Bernstein is pristine. It's never been this close to the Sun before. Its surface still contains super-volatile ices like carbon monoxide, preserved from the formation of the solar system 4.6 billion years ago. This is a time capsule, a frozen archive of the primordial solar nebula falling inward for the first time in recorded history. And here's the part that should make you sit up and pay attention. This thing has barely woken up yet. It's still beyond the orbit of Uranus. It won't reach perihelion, its closest approach to the Sun, until January of 2031, and even then, it's only going to get as close as 10.9 AU, just inside the orbit of Saturn. That's still incredibly far. But it's close enough that the outgassing will intensify, the jets will strengthen, and if the subsurface ice has been building pressure for millions of years, there's no telling what will happen when the Sun's warmth finally penetrates deep enough to trigger a full-scale eruption. We're not watching a comet die, we're watching one wake up for the very first time. Part 4, the Florida problem. Humans are spectacularly bad at understanding cosmic scale. We evolved to comprehend things we can see, touch, and walk around. A mountain is big, an ocean is vast, but when you start talking about objects measured in hundreds of kilometers, floating billions of miles away, the numbers stop meaning anything. Your brain just shuts down. It's too big, too far, too abstract. So let me try to fix that problem by giving you a comparison that might actually stick. Right now, the astronomical community is buzzing about C/2024S1, also known as 3I/Atlas, a comet currently making its way through the inner solar system. Estimates suggest it's roughly 10 kilometers in diameter. To put that in human terms, imagine Mount Everest. Picture that towering summit, 8.8 kilometers above sea level. 3I/Atlas is roughly that size. It's a mountain in space, a frozen Everest tumbling through the void. And if you stood on its surface, you'd feel like you were standing on a world. A small world, sure, but a world nonetheless. Now take that mountain, that 10-kilometer comet, and multiply it by 14. Not 14 times heavier, 14 times wider, because Bernardinelli-Bernstein is approximately 130 kilometers across. To give you a geographic anchor, the state of Florida measures roughly 200 kilometers wide at its broadest point. Bernardinelli-Bernstein is 2/3 the width of Florida. It's not a mountain anymore. It's a landscape. It's a frozen territory floating through space, massive enough that if you stood on one side, the opposite horizon would be dozens of kilometers away. But here's where the math gets truly disturbing. Mass doesn't scale linearly with diameter. It scales with volume, and volume grows exponentially. If you double the diameter of a sphere, you increase its volume by a factor of 8. So when you go from 10 kilometers to 130 kilometers, you're not just dealing with something 13 times bigger. You're dealing with something exponentially more massive. The current estimates, depending on density assumptions, suggest that Bernardinelli-Bernstein could be over 1,000 times more massive than 3I/Atlas. Not 13 times, 1,000 times. That's the difference between a boulder and a mountain range. Let's talk about thermal inertia, because that's what makes large objects behave so differently from small ones. When you put an ice cube in the sun, it melts quickly. The heat penetrates rapidly because the ice cube has very little mass. But when you put a glacier in the sun, it takes months or years to melt. The sheer volume of ice acts as a thermal buffer, resisting temperature changes. Bernardinelli-Bernstein isn't an ice cube. It's a glacier. It's a frozen world so massive that the sun's warmth can only penetrate a few meters into the surface at most. The interior remains untouched, preserved at the temperature of deep space, potentially as cold as 20 to 30 degrees Kelvin. This is why the term world eater keeps appearing in informal discussions among astronomers, even though it's not a technical term. It's a metaphor borrowed from science fiction, but it captures something essential about scale. This isn't a comet in the traditional sense. It's a rogue planetoid, a frozen moon that escaped from somewhere beyond Neptune and is now falling inward. carried by the Sun's gravity. And if it were on a collision course with Earth, which it absolutely is not, the impact would be measured not in megatons or gigatons, but in exotons. It would be an extinction-level event that would make the Chicxulub impactor look small by comparison. Before you panic, let me be extremely clear. Bernardinelli-Bernstein is not going to hit Earth. Its orbit has been calculated with extraordinary precision. At its closest approach in 2031, it will be nearly 11 astronomical units away, roughly 1 billion miles from our planet. There is zero impact risk. None. But the existence of an object this size falling inward from the Oort Cloud forces us to confront an uncomfortable question. What else is out there? How many other Bernardinelli-Bernsteins are drifting through the outer solar system, too far and too dark to detect, until they suddenly aren't? The danger isn't this comet. The danger is the category it represents. Part 5. King of Comets. For decades, the title of most dangerous object known to humanity has belonged to Comet Swift-Tuttle. Discovered in 1862 and rediscovered in 1992, Swift-Tuttle is a periodic comet, roughly 26 kilometers in diameter. It orbits the Sun every 133 years, and its path occasionally brings it uncomfortably close to Earth's orbit. Not close enough to hit us anytime soon, but close enough that scientists have calculated a small but non-zero probability of impact in the distant future, possibly in the year 4479. If Swift-Tuttle ever did collide with Earth, the energy release would be equivalent to roughly 27 times the event that killed the dinosaurs. It's a legitimate nightmare scenario, and that's why it holds its fearsome reputation. But here's the problem with calling Swift-Tuttle the most dangerous object. It's only dangerous because of its orbit, not its size. A 26-kilometre comet on a collision course is catastrophic, yes, but a 130-kilometre comet on a collision course? That's not an extinction event. That's a planetary reset button. That's the difference between wiping out most life on Earth and wiping out the conditions that allow life to exist at all. And Bernardinelli-Bernstein is nearly 5 times wider than Swift-Tuttle. Let's put this in geological context. The Chicxulub impactor, the asteroid that ended the Cretaceous period and killed the non-avian dinosaurs 66 million years ago, is estimated to have been roughly 10 to 15 kilometers in diameter. That single impact released energy equivalent to about 10 billion Hiroshima bombs. It created a crater 180 kilometers wide. It ejected so much debris into the atmosphere that the sky darkened for months, possibly years. Global temperatures plummeted. Photosynthesis stopped. The food chain collapsed from the bottom up. 3/4 of all species on Earth went extinct. Bernardinelli-Bernstein is approximately 9 to 13 times wider than the Chicxulub impactor. If you scale up the diameter by a factor of 10, you scale up the volume by a factor of 1,000. Even accounting for differences in density, comets are typically less dense than asteroids. Bernardinelli-Bernstein likely carries hundreds of times more mass than the object that killed the dinosaurs. An impact from something this size wouldn't just cause an extinction event, it would sterilize large portions of the planet. The oceans would boil, the crust would crack, the atmosphere would be blown partially into space. We're talking about an impact that would fundamentally alter Earth's geology, not just its biology. But here's the question. Nobody seems to be asking loudly enough. Why are we so focused on near-Earth objects when the real monsters are in the outer solar system? The institutional focus on planetary defense has always prioritized fast-moving asteroids in Earth-crossing orbits. And that makes sense. Those are the immediate threats, the ones with short warning times and frequent close approaches. But the assumption embedded in that focus is that large impactors are rare, that we've already found most of them, and that anything big enough to be truly catastrophic will be detected with plenty of time to respond. Bernardinelli-Bernstein proves that assumption is flawed. This object was sitting in archival data for 7 years before anyone realized what it was, and it's enormous. It's not hiding in the asteroid belt, it's not lurking in some obscure near-Earth orbit. It came from the Oort Cloud, a region so distant and so poorly surveyed that we have no idea how many more objects like this exist. The size-based threat model has a blind spot, and that blind spot is shaped exactly like Bernardinelli-Bernstein. So yes, Comet Swift-Tuttle is dangerous, because its orbit might someday intersect Earth's. But Bernardinelli-Bernstein is dangerous for a different reason. It reveals that our survey systems are not designed to catch slow-moving giants until they're already well into the inner solar system. by the time we spotted this one, it had been approaching for millions of years. We didn't discover it. We stumbled across it in old data, and then spent years figuring out what it actually was. That's not a detection system. That's an audit failure. And if Bernardinelli-Bernstein is the king of comets, then the real question is this: how many others are waiting in the outer darkness, drifting inward, uncatalogued and unnamed? Part 6. An Oort Cloud that shouldn't exist. Let's talk about the place where Bernardinelli-Bernstein comes from, because the Oort Cloud isn't just distant, it's hypothetical. We've never actually seen it. We infer its existence the way you infer a hurricane by watching leaves blow across the street. Comets arrive from random directions, falling inward on long elliptical orbits that trace back to a spherical shell surrounding the solar system. The math demands that something out there is acting as a reservoir, a gravitational storage facility holding billions or perhaps trillions of icy bodies at distances between 2,000 and 100,000 astronomical units. That's the Oort Cloud. A spherical halo of frozen debris left over from the formation of the solar system, preserved in deep freeze for 4.6 billion years. The traditional model says the Oort Cloud should contain mostly small objects, a few kilometres across, maybe 10. These are the shattered remnants of the protoplanetary disk, icy pebbles and boulders that got ejected during the chaotic early days when Jupiter and Saturn were still migrating through the solar system, flinging debris in every direction. The idea that something 130 kilometres wide could be lurking out there wasn't part of the plan. Objects that large should have either accreted into planets or been ejected entirely from the solar system. They shouldn't be sitting quietly in the Oort Cloud waiting to fall back inward. But Bernardinelli-Bernstein exists, which means the mass budget for the Oort Cloud is wrong. If there's one object this size, there are probably more. And if there are more, then the total mass of the Oort Cloud is significantly higher than we thought. That has implications. It means the early solar system was even more violent than models suggest. It means planetary migration threw more material outward than we calculated. It means the Oort Cloud isn't just a graveyard for small debris. It's a holding tank for planetary building blocks that never finish the job. How did something this large end up so far from the Sun? The most plausible explanation involves the early chaos of planetary formation. 4.5 billion years ago, the solar system was a shooting gallery. Jupiter, Saturn, Uranus and Neptune weren't in their current positions. They were closer to the Sun, still accreting mass, still interacting gravitationally with the disk of planetesimals that surrounded them. And those interactions were violent. Objects got flung inward toward the Sun. Objects got ejected into interstellar space. And some objects got thrown into extremely long orbits, far enough that the Sun's gravity barely held them, but close enough that they didn't escape entirely. Planetary migration models suggest that Neptune moved outward significantly during the first few 100 million years of the solar system's history. As it migrated, it ploughed through a dense population of icy bodies, scattering them in every direction. Most got ejected, some crashed into the inner planets, but a small percentage ended up in stable orbits at extreme distances, their perihelia close enough to feel the Sun's pull, but their aphelia so far away that they spend most of their time in the freezing darkness. Bernardinelli-Bernstein likely formed somewhere between the orbits of Uranus and Neptune, accreted to its current size, and then got kicked outward by a close encounter with one of the ice giants. But there's another possibility, and it's more speculative but fascinating. What if Bernardinelli-Bernstein didn't form in our solar system at all? What if it was captured? Stars don't form in isolation. They form in clusters, dense groups of hundreds or thousands of newborn stars all packed into a relatively small volume of space. And during those early days, before the cluster disperses, stellar flybys are common. Another star passes within a few hundred or a few thousand astronomical units of the Sun, close enough that its gravity can strip away loosely bound objects or donate some of its own debris into the Sun's influence. If that happened, if Bernardinelli-Bernstein came from another star system and was captured by the Sun during a close encounter, then it's not just a relic of our solar system's formation. It's a piece of someone else's solar system, trapped in orbit around our Sun. That would explain why it's so large. It wouldn't have been subject to the same collisional grinding that pulverized most Oort Cloud objects. It would have arrived fully formed, a frozen world from another system, and we'd never know unless we could somehow sample its composition and compare it to the isotopic ratios of native solar system material. None of this is proven. It's all plausible, All consistent with the data we have, but there's no smoking gun. And that's the frustrating part. Bernardinelli-Bernstein raises more questions than it answers. Where did it come from? How many more objects like it exist in the Oort Cloud? Is it a fluke, a 1 in a billion statistical outlier, or is it the first member of a population we never knew existed? The only way to answer those questions is to keep looking, to survey the outer solar system more thoroughly, to check the archives for other misidentified objects, because if there's one Bernardinelli-Bernstein, there might be 10, and if there are 10, we need to know where they are and where they're going. Part 7. Is this thing even a comet? Here's a question that sounds simple but unravels into philosophical chaos the moment you start pulling at the threads. What makes something a comet? The textbook answer is straightforward. A comet is a small icy body that releases gas and dust when it approaches the sun, creating a visible coma and sometimes a tail. Asteroids, by contrast, are rocky or metallic and don't outgas. Planets are large enough to have cleared their orbits of debris and have sufficient mass to pull themselves into spherical shapes through their own gravity. Easy, right? Except when you actually start applying those definitions to real objects in the solar system, the categories collapse immediately. Take Pluto. For 76 years it was a planet. Then in 2006, the International Astronomical Union redefined the term planet to require that an object has cleared the neighbourhood around its orbit, and Pluto got demoted to dwarf planet. Except Pluto shares its orbital space with thousands of other Kuiper Belt objects, so by that definition it doesn't qualify. But then neither does Neptune, technically, because Neptune hasn't cleared Pluto from its orbital path. The point is, classification systems are human constructs. They're tools for organising information, but the universe doesn't care about our categories, and Bernardinelli-Bernstein is proving that point in spectacular fashion. Is it a comet? It's outgassing. It has jets of carbon monoxide streaming off its surface. It comes from the Oort Cloud, the reservoir that supplies long-period comets. So, yes, by the traditional definition it's a comet. But it's also 130 kilometres wide, which puts it in the size range of small dwarf planets, and it behaves more like a world than a comet. Its gravity is strong enough to influence the outgassing patterns. It has thermal inertia comparable to a planetary body. And if you removed the thin layer of surface ice and looked at the interior, you'd probably find a mix of rock and ice, compacted under its own weight into something denser and more structured than a typical comet nucleus. So maybe Bernardinelli-Bernstein is a transitional body, something that sits on the boundary between comets and dwarf planets, belonging fully to neither category. Astronomers have a name for objects like this: centaurs. They're icy bodies that orbit between Jupiter and Neptune, too far out to be asteroids, too close in to be classical Kuiper Belt objects, and occasionally exhibiting comet-like activity. Bernardinelli-Bernstein started as a centaur-like object billions of years ago, before its orbit decayed and it began falling inward. But calling it a centaur doesn't really solve the problem, it just kicks the can down the road. Here's a more provocative idea. What if Bernardinelli-Bernstein is a failed planet core? During the formation of the solar system, planetary embryos collided and merged to form the terrestrial planets and the cores of the gas giants. But not every embryo succeeded. Some got scattered before they could grow large enough to dominate their orbits. Some got ejected into the Oort Cloud, frozen in time, never completing the journey to planethood. Bernardinelli-Bernstein might be one of those leftover cores, a frozen relic of a planet that never was, now falling back toward the sun after billions of years in exile. If that's true, then the distinction between comet and planet becomes even murkier, because the only difference between Bernardinelli-Bernstein and a dwarf planet like Ceres is that Bernardinelli-Bernstein retained a thick shell of volatile ices, while Ceres lost most of its volatiles early in its history. Structurally, they might be nearly identical, a rocky core surrounded by an icy mantle, with surface features shaped by impacts and outgassing. But we call one a dwarf planet and the other a comet, purely based on where they orbit and whether they outgaze. The taxonomy falls apart under scrutiny. Why does this matter? Because the way we classify objects influences the way we study them and the way we assess risk. If Bernardinelli-Bernstein is just a comet, then it gets filed under cometary science, and the focus is on outgassing dynamics and dust production. But if it's a planetary body, then the focus shifts to internal structure, differentiation, and long-term evolution. And if we're trying to understand the threat landscape of the outer solar system, classification isn't just academic. It determines which survey programs get funded, which observation strategies get prioritized, and which objects get flagged as high priority targets. There's a broader lesson here that connects to exoplanet science. As we've discovered thousands of planets around other stars, we've found that the categories we invented for our own solar system don't apply. Hot Jupiters shouldn't exist, but they do. Super-Earths don't exist in our system, but they're common elsewhere. Mini-Neptunes, water worlds, lava planets, rogue planets floating in the void with no star at all. The universe produces every possible variation on the theme of stuff orbiting other stuff, and our job isn't to force those objects into neat boxes. Our job is to describe what they actually are, even if that means admitting that our definitions were always provisional and incomplete. Bernardinelli-Bernstein is teaching us that lesson the hard way. It's not a comet. It's not a dwarf planet. It's something in between, something we don't have a perfect name for yet. And that's okay. The universe is under no obligation to fit our taxonomy. Part 8. The silence before the jets. There's something deeply unsettling about watching a massive object wake up slowly. Bernardinelli-Bernstein isn't exploding. It's not fragmenting. It's just quietly outgassing carbon monoxide at 16 to 20 astronomical units, a distance where most comets wouldn't show any activity at all. And the reason that's unsettling is because we don't know when the real activity begins. We don't know at what distance the subsurface ice starts to sublimate fast enough to crack the crust. We don't know if there are pockets of trapped volatiles under pressure, waiting to burst like champagne bottles. We're watching the opening act of a process that will take another decade to fully unfold, and we have no script. Thermal lag is the key to understanding why Bernardinelli-Bernstein's activity is so delayed. Imagine you're heating a thick steak on a grill. The surface sizzles immediately, but the centre stays cool for minutes. Heat doesn't propagate instantly. It diffuses slowly, conducted from molecule to molecule, and the thicker the material, the longer it takes. Bernardinelli-Bernstein has been falling toward the Sun for millions of years, but only in the last few millennia has it gotten close enough for solar radiation to start warming the surface, and that heat is still working its way inward, centimetre by centimetre, sublimating surface ices and creating pressure in the subsurface layers. Here's what keeps planetary scientists awake at night. We don't know how stable the crust is. Comets fragment all the time. Shoemaker-Levy 9 broke into more than 20 pieces before it crashed into Jupiter in 1994. Comet Linear disintegrated in 2000. Comet Eson didn't survive its close pass by the Sun in 2013. But those were small comets, a few kilometres across, with weak gravitational binding and porous, fragile structures. Bernardinelli-Bernstein is different. Its gravity is strong enough to hold itself together against most stresses. But if the subsurface ice builds up enough pressure, if there are structural weaknesses from ancient impacts, if the thermal stresses exceed the tensile strength of the ice rock matrix, then even a massive object like this could fracture. Fragmentation isn't necessarily catastrophic. It doesn't mean the entire object explodes. More likely it means pieces carve off, like icebergs breaking away from a glacier. A chunk a few kilometres across shears off, continues on a slightly different trajectory, and suddenly you have two objects instead of one. And if that happens, the observational picture changes immediately, because the newly exposed interior would start outgassing at a much higher rate, and the fragment would develop its own coma and tail. It would be spectacular, and it would also make tracking the object more complicated, because you'd have to account for non-gravitational forces, the subtle pushes from outgassing that alter the orbit in unpredictable ways. But here's the scenario that nobody talks about openly because it sounds too much like science fiction. What if Bernardinelli-Bernstein doesn't fragment at all? What if it stays intact all the way to perihelion, 10.9 astronomical units from the Sun, still beyond Saturn, and then the outgassing intensifies to levels we've never observed before? What if the jets become so powerful that they lift dust and ice off the surface, creating a coma hundreds of thousands of kilometres wide? What if the solar wind pushes that material into a tail that stretches across the inner solar system visible from Earth with the naked eye? A comet the size of Florida, glowing like a second moon, reminding everyone who looks up that the sky is not empty and the universe is not tame. That's not a prediction. It's a possibility. The truth is, we don't have a good model for what a 130-kilometre comet does when it gets close to the Sun because we've never seen one before. Every comet we've studied in detail has been small enough that its gravity is negligible. The outgassing dynamics are dominated by surface processes, but with Bernardinelli-Bernstein, gravity matters. The object can hold onto some of its own atmosphere. The subsurface structure matters. The thermal history matters. And all of those variables introduce uncertainty into the predictions. We're making educated guesses based on physics, but we won't know for sure until it happens. And then there's the quiet fear that nobody says out loud, but everyone who works on this problem thinks about occasionally. What if there's a delayed eruption? What if, after perihelion, after Bernardinelli-Bernstein starts heading back out toward the Oort Cloud, the accumulated heat finally penetrates deep enough to trigger a massive outburst? What if, 10 years from now, this object suddenly brightens by several magnitudes, not because it's getting closer to the Sun, but because something inside finally reached critical pressure? It would be spectacular. It would also be a reminder that comets are not inert. They're dynamic, evolving, unpredictable. And when you scale them up to planetary sizes, the unpredictability scales with them. Part 9. The surveillance gap. Let's talk about the elephant in the room, or rather, the elephant slowly drifting through the outer solar system that nobody noticed for 7 years. Bernardinelli-Bernstein was discovered in archival data from the Dark Energy Survey, a project that wasn't even looking for solar system objects. It was an accidental discovery, a happy accident where someone decided to sift through old images and see what had been overlooked. And what they found was the largest comet ever detected, already well into the inner solar system, and nobody had raised an alarm because nobody knew it was there. That's not a success story. That's a systems failure. Here's how survey astronomy works. Telescopes scan the sky repeatedly, taking images of the same patches of sky days or weeks apart. Software compares the images, looking for objects that have moved. Asteroids and comets move relatively quickly compared to distant stars, so they stand out. The software flags them. Humans review the flags. Objects get catalogued. Orbits get calculated. Threats get assessed. It's a pipeline, and it's designed to catch fast-moving near-Earth objects, but it's not designed to catch slow-moving giants in the outer solar system. Because the assumption has always been that slow-moving objects are either far away and harmless or already known, Bernardinelli-Bernstein breaks that assumption. It was moving slowly, yes, but that's because it was far away. And it was far away because it came from the Oort Cloud, not the asteroid belt. The survey systems flagged it, but not as a priority. It didn't cross Earth's orbit. It didn't show comet-like activity initially. It just looked like another distant Kuiper belt object, worth cataloguing but not worth urgent follow-up. And so it sat in the database, unrecognised for what it was, until someone with the right expertise looked closer. The Vera Rubin Observatory, previously known as the Large Synoptic Survey Telescope or LSST, is designed to fix some of these problems. It's scheduled to begin operations soon, and when it does, it will survey the entire visible sky every few nights, generating an unprecedented flood of data. The goal is to detect everything that moves, from near-Earth asteroids to distant trans-Neptunian objects, and to do it fast enough that follow-up observations can confirm orbits and assess risks in near real time. It's ambitious, it's necessary, but it's not a magic bullet. Even with the Vera Rubin Observatory online, there will still be a surveillance gap, because detecting an object is not the same as characterizing it. You can find a new dot moving across the sky, but you need multiple observations over weeks or months to calculate its orbit accurately. You need spectroscopy to determine its composition. You need photometry to estimate its size and albedo. And if the object is far away, if it's beyond 20 or 30 astronomical units, all of those measurements become harder. The light is faint, the signal is weak, and the time required to gather enough data stretches from weeks into months or years. Bernardinelli-Bernstein's orbit is well understood now because we have observations spanning multiple years. We know it's not going to hit Earth. We know it's perihelion. We know when it will start heading back outward. But imagine if we'd discovered it only a few months ago, not 7 years ago. Imagine if we'd found it when it was already at 15 or 16 astronomical units, with less than a decade until perihelion, and we didn't have a complete orbital solution yet. The uncertainty would be enormous. We wouldn't know if it was on a collision course or not. We'd have to wait for more observations, and during that waiting period, people would panic. Because that's what people do when the sky reveals something enormous and poorly understood. This is the late discovery problem. It's not enough to eventually find every object in the solar system. We need to find them early, when they're still far away, when we have time to study them and calculate their orbits with precision. Because warning time matters more than distance. An asteroid detected 6 months before impact is far more dangerous than an asteroid detected 20 years before impact, even if the latter is intrinsically larger. Time is the critical resource, and the way our survey systems are currently designed, we're optimizing for fast-moving objects close to Earth, not slow-moving giants in the outer solar system. That's the gap. And Bernardinelli-Bernstein fell right through it. Funding priorities are part of the problem. Planetary defense programs focus on near-Earth object detection because that's where the imminent risk is. Nobody's worried about a comet that won't reach perihelion for another decade. But the imminent risk is not the same as the total risk. And if we're going to take planetary defense seriously, if we're going to claim that we can protect Earth from cosmic threats, then we need to be honest about the limits of our current capabilities. We can't deflect a 130-kilometre object. We can't even track them reliably until they're already close. And if there are more objects like Bernardinelli-Bernstein drifting inward, undetected and uncatalogued, then our sense of security is an illusion. Part 10. The conspiracy nobody needs. Let me address the conspiracy theories now before they spin out of control. There's always someone who looks at a story like Bernardinelli-Bernstein and decides that the official narrative is hiding something. The government knows more than they're telling us. This object isn't natural. It's a ship. It's a weapon. It's a sign. And the fact that it was discovered in archival data, not announced immediately, only fuels the suspicion. Why did it take 7 years to tell us? What else are they hiding? The answer is boring and procedural and completely unsatisfying to anyone who wants drama. It took 7 years because scientific research takes time. Nobody was hiding anything. The data was public. The discovery was announced in peer-reviewed papers. There's no conspiracy, but that won't stop people from believing there is. Here's the irony. The natural explanation for Bernardinelli-Bernstein is scarier than any alien narrative. If this were an artificial object, if some advanced civilization had built a massive ship and sent it toward the inner solar system, then at least we'd know it was controlled. It would have a purpose. It would follow predictable rules. But Bernardinelli-Bernstein isn't controlled. It's a frozen relic of planetary formation, falling inward because gravity doesn't care about human convenience. It's chaotic. It's mindless. And there are probably more objects like it out there, drifting through the darkness, waiting for us to stumble across them. That's the part that should terrify you, not aliens, nature. Scientific conservatism plays a role in how discoveries like this get communicated to the public. When you're an astronomer and you find something unusual, you don't immediately call a press conference and announce that the sky's falling. You check your math. You verify the observations. You write a paper. You submit it to a journal. You wait for peer review. You respond to reviewers' comments. You revise the paper. And then, maybe 6 months or a year later, the paper gets published. And only then does the wider community learn about the discovery. That's not a cover-up. That's how science works. But it creates a perception problem, because by the time the public hears about it, the discovery is old news to the researchers. Publication bias is another issue. Journals want to publish exciting results, things that challenge existing models or reveal new phenomena. But they're less interested in papers that say, "We looked for X and didn't find it." So there's an incentive to emphasize the dramatic aspects of a discovery and downplay the uncertainties. Bernardinelli-Bernstein is the largest comet ever found, so it gets published. But the hundreds of surveys that didn't find giant comets, those don't get papers. And that creates a distorted picture of the threat landscape, because we hear about the one spectacular object but not about the empty searches that suggest such objects are rare. Career incentives matter too. Astronomers are rewarded for discoveries, not for refining existing catalogues. If you find a new object, you get your name on it. Bernardinelli and Bernstein will be remembered because their names are literally attached to this comet. But if you spend 5 years improving orbital calculations for known objects, reducing uncertainties and making the catalogue more reliable, nobody cares. There's no glory in maintenance work. So the system incentivizes discovery over characterization, which means we keep finding new things without fully understanding the things we've already found. And that's how objects like Bernardinelli-Bernstein sit in databases for years before anyone realizes what they are. And then there's the comforting lie that people keep repeating. We'd see it coming. If something truly dangerous were headed our way, we'd detect it years in advance and have time to respond. Except Bernardinelli-Bernstein proves that's false. We didn't see it coming. We found it in old data after it had already been approaching for millions of years. And even now, with our best telescopes and our most sophisticated survey programs, we're still limited by the speed of light and the faintness of distant objects. There are things out there right now, massive and dangerous, that we won't detect until they're already close. And when that happens, the warning time won't be years. It might be months or weeks. Institutional inertia is the final piece of the puzzle. Space agencies and planetary defense programs operate on budgets and timelines set years in advance. They have priorities and protocols, and those priorities are based on threat assessments that assume the outer solar system is mostly empty and harmless. Bernardinelli-Bernstein challenges that assumption, but changing institutional priorities requires more than one discovery. It requires sustained evidence, political will, and funding. And none of that happens quickly. So even if astronomers are now convinced that we need to survey the outer solar system more thoroughly, even if the data clearly shows a surveillance gap, it will take years before those concerns translate into new telescopes and expanded survey programs. There are no villains here, just systems that move slowly, and a universe that doesn't wait for us to catch up. Part 11. This month's exoplanet that shouldn't exist. Every few months, astronomers announce the discovery of an exoplanet that breaks the rules, a Jupiter-sized planet orbiting so close to its star that its surface is molten. A rocky planet 10 times the mass of Earth, too large to be terrestrial but too dense to be a gas giant. A planet orbiting a binary star system in a configuration that shouldn't be stable. And every time, the scientific community has the same reaction. How is this possible? Followed quickly by, what else don't we know? Recently, astronomers detected a massive exoplanet in a system that defies current formation models. The planet's mass suggests it should have migrated inward and crashed into its star millions of years ago. But it's still there, orbiting serenely, as if the laws of orbital mechanics decided to take a day off. The discovery was published, papers were written, and theorists scrambled to explain how a planet this massive could exist in this configuration. And the answer, as usual, is that we don't fully understand planet formation. We have models, we have simulations. But the universe keeps producing exceptions. This is the same problem we have with Bernardinelli-Bernstein. According to our models, objects 130 kilometers wide shouldn't be common in the Oort Cloud. The mass budget doesn't allow for it. The formation scenarios don't produce them in large numbers. And yet, there it is. Massive, pristine, and falling inward. Which means either Bernardinelli-Bernstein is a statistical fluke, a 1 in a trillion outlier, or our models are missing something fundamental. And given how often exoplanet discoveries have proven our models wrong, I'm betting on the latter. The connection between Bernardinelli-Bernstein and exoplanet science is deeper than it might seem. When we look at debris disks around other stars, we see structures that resemble our Kuiper belt and Oort cloud, and those disks contain mass. Lots of it. More mass than our models predict should be left over after planet formation, which suggests that planetary systems don't efficiently sweep up all the debris. There are always leftovers, and some of those leftovers are large, planet-sized potentially, just sitting in the outer reaches of the system, too far from the star to be easily detected, slowly drifting through the darkness. If that's true, then every planetary system has its own population of Bernardinelli-Bernsteins, frozen worlds and near worlds scattered into distant orbits during the chaotic early days of planet formation, waiting to fall back inward. Some will be ice giants, some will be rocky cores, some will be hybrid objects, massive enough to hold themselves together, but not massive enough to clear their orbits. And we'll never see most of them because they're too far away and too dark. We'll only detect them when they happen to pass through our line of sight, or when they reflect enough starlight to be visible in infrared surveys. The broader lesson is this. Our solar system is not special. For a long time, we assumed it was. We assumed that planetary systems came in one flavour, something like ours, with rocky planets close in and gas giants farther out, and maybe a debris disk beyond that. But exoplanet science has taught us that planetary systems are wildly diverse. Hot Jupiters, super-Earths, mini-Neptunes, systems with 7 terrestrial planets packed into tight orbits, systems with massive planets on extremely elliptical paths, rogue planets floating in interstellar space with no star at all. The universe experiments with every possible configuration, and that means the outer regions of planetary systems, the Oort Cloud, equivalents around other stars, are probably full of massive objects we can't detect yet. Bernardinelli-Bernstein is forcing us to confront the same realization that exoplanet science has been hammering home for 2 decades. The universe is not obligated to conform to our expectations. Our models are approximations, our categories are provisional, and every time we build a more sensitive telescope or analyze a deeper data set, we find something that doesn't fit. That's not a failure of science. That's science working exactly as it should, constantly updating its understanding as new data arrives. But it's also a reminder that humility is the correct stance when dealing with the cosmos. We know less than we think, and the gaps in our knowledge are larger than the discoveries we've made. Part 12. AI is now discovering objects. Humans miss. Pattern recognition is something the human brain excels at under certain conditions. If you show someone a photo of a dog and a photo of a cat, they can tell you immediately which is which, even if they've never seen those specific animals before. That's because our brains evolved to extract meaningful patterns from complex visual data. But there's a catch. We're only good at recognizing patterns we've been trained to see. Show someone a spectrogram of a pulsar signal, and they'll have no idea what they're looking at. The pattern is there. The data contains the information. But without training, without context, the human brain can't extract it. Our visual system is optimized for survival in the African savanna, not for analyzing astronomical data. We're excellent at detecting motion in our peripheral vision, at distinguishing faces from backgrounds, at recognizing the difference between a stick and a snake. These capabilities kept our ancestors alive, but they don't translate well to scientific analysis. When you're looking at thousands of grayscale images of star fields, each containing millions of pixels, your pattern recognition system gets overwhelmed. The brain tries to impose familiar structures on random noise. It sees faces in clouds. It finds meaning in static. And critically, it gets fatigued. After reviewing 100 images, attention wavers. After 1,000, errors creep in. The human brain simply wasn't designed for this kind of repetitive analytical work. That's where artificial intelligence comes in. Machine learning algorithms, particularly neural networks, are exceptionally good at finding patterns in large data sets, including patterns that humans would miss. You feed the algorithm thousands of examples, labelled images of asteroids versus stars versus cosmic rays versus noise, and it learns to distinguish between them. Then you turn it loose on new data, and it flags objects that match the patterns it learned. And because the algorithm doesn't get tired, doesn't get bored, and doesn't make assumptions about what it's supposed to find, it catches things humans overlook. The architecture of neural networks mimics the structure of biological brains, but without the limitations. Artificial neurons connect in layers, each layer learning to recognize increasingly complex features. The first layer might identify edges and gradients. The second layer combines those edges into shapes. The third layer recognizes those shapes as meaningful objects, and the final layers classify those objects into categories: asteroid, star, artifact, noise. The training process involves showing the network millions of examples, adjusting the connections between neurons until the network reliably produces correct answers. It's brute force learning, but it works remarkably well. In astronomy, AI is already revolutionizing how we process data. The Zwicky Transient Facility uses machine learning to identify supernovae in real time, sifting through thousands of images every night and flagging transient events for follow-up. The Kepler Space Telescope used AI to identify exoplanet candidates in light curves, finding planets that traditional algorithms missed. And now, researchers are training neural networks to identify slow-moving objects in archival data, precisely the kind of objects that slip through traditional survey pipelines. Objects like Bernardinelli-Bernstein. The success stories are compelling. In 2017, researchers at Google and the University of Texas used a neural network to discover 2 previously unknown exoplanets in Kepler data that had already been analysed by conventional algorithms. The planets were there all along, visible in the light curves, but the traditional software had flagged them as false positives because the signals didn't quite match the expected profile. The neural network, trained on thousands of confirmed exoplanets, recognised the pattern despite the anomalies. Those planets are now confirmed and catalogued. That's not replacing human astronomers. That's augmenting them, giving them tools to find what they otherwise would have missed. Here's the provocative question. Could AI have flagged Bernardinelli-Bernstein earlier? If someone had trained a neural network to recognise the subtle motion of distant trans-Neptunian objects in dark energy survey data, could it have identified the object years before humans did? The answer is probably yes. Not certainly, because AI isn't magic. It can only find patterns it's been trained to recognise. But if the training set included examples of slow-moving outer solar system objects, then the algorithm would have flagged Bernardinelli-Bernstein as anomalous, unusually bright for its motion, unusual orbital characteristics, worth a closer look. The key advantage of AI in this context is consistency. Humans get distracted. We prioritise certain types of objects based on what we think is important. We might look at a slowly moving object and dismiss it as uninteresting because it doesn't cross Earth's orbit, doesn't have a tail, doesn't fit our mental model of what a hazardous object looks like. But an AI trained to flag all unusual combinations of brightness and motion wouldn't make that judgment call. It would flag the object, period, and then humans could decide whether to follow up. That division of labour, AI handling the tedious screening work and humans handling the interpretation and decision-making, is where the real power lies. The data deluge problem is only getting worse. The Vera Rubin Observatory will generate approximately 20 terabytes of data every night once it's fully operational. That's more data than the entire astronomy community can process manually. Humans can't review every image. We can't visually inspect every light curve. We need automated systems to filter the data, prioritise targets, and flag anomalies. And those systems will increasingly rely on AI, which means the future of discovery is not humans staring at images through telescopes. It's algorithms sifting through petabytes of data, looking for patterns that even the researchers who built the algorithms didn't anticipate. Consider the scale. 20 terabytes per night is roughly 20,000 gigabytes. That's equivalent to about 5,000 hours of high-definition video every single night. Over the course of a year, the Vera Rubin Observatory will generate data equivalent to millions of hours of footage. No human team, no matter how large, can review that volume of information. The only solution is automation. And the best automation we have for complex pattern recognition tasks is machine learning. So whether we like it or not, AI is going to become the first line of analysis for astronomical surveys. Humans will review what the AI flags, but the AI will do the initial screening. But there are risks. AI systems are only as good as their training data, and if the training data is biased, the AI will be biased. If you train a neural network to identify asteroids using examples from the inner solar system, it might miss comets from the Oort Cloud because they look different. The algorithm will flag what it's been taught to see and ignore everything else. That's why transparency matters. We need to know what data these systems are trained on, what patterns they're optimized to detect, and what blind spots remain. Because the last thing we want is to build an AI-powered survey system that's exceptionally good at finding one type of object and completely blind to another. Training bias is a subtle problem. Imagine you're building a neural network to identify potentially hazardous asteroids. You gather examples from the existing catalogue, thousands of confirmed asteroids with known orbits. You train your network on those examples. It learns what asteroids look like in survey images. Then you deploy it on new data, and it works great at finding more asteroids that look like the ones in the training set. But what about asteroids that don't look like the training examples? What about comets with unusual activity patterns? What about objects from interstellar space with hyperbolic orbits? If your training data doesn't include those edge cases, your AI won't flag them. It will classify them as noise or artifacts and move on. The solution is diverse training sets and continuous validation. You need examples of every type of object you care about: main belt asteroids, near-Earth asteroids, comets, centaurs, trans-Neptunian objects, maybe even interstellar visitors, and you need to regularly test your AI against new discoveries to make sure it's catching things it should catch. If a new object gets discovered by humans that the AI missed, you investigate why. You add similar objects to the training set. You retrain the network. It's an iterative process, not a one-time setup. Explainability is another challenge. Neural networks are often described as black boxes. You feed data in one end, and predictions come out the other. But understanding why the network made a particular decision is difficult. The weights and connections between millions of artificial neurons don't correspond to human-readable logic. They're optimized patterns that work but can't be easily explained. That creates problems when you need to trust the AI's judgment. If the network flags an object as potentially hazardous, do you commit resources to follow up observations? Or do you need to understand why it flagged the object before you take it seriously? The lack of explainability creates friction in the human-AI collaboration. Researchers are working on this problem. Newer AI architectures include attention mechanisms that highlight which parts of the input data the network focused on when making its decision. If the network flags an object as unusual, you can look at the attention map and see that it was responding to a specific combination of brightness and motion characteristics. That helps build trust. It lets humans verify that the AI is making decisions for the right reasons, not just picking up on spurious correlations in the training data. The flip side is that AI could accelerate discovery at a pace we've never seen before. Archival data from decades of surveys is sitting in databases right now, waiting to be reanalyzed with modern algorithms. Objects that were too faint to detect with older software might be visible to neural networks trained on more recent data. Patterns that humans dismissed as noise might be real signals. And if someone unleashes a well-trained AI on those archives, we might discover dozens or hundreds of new objects that have been hiding in plain sight for years. Objects like Bernardinelli-Bernstein, objects that could rewrite our understanding of the outer solar system, objects that might be on trajectories we need to know about. This is not hypothetical, it's already happening. Teams are applying modern machine learning techniques to old datasets and finding new objects. The Pan-STARRS survey, the Sloan Digital Sky survey, even older photographic plate archives from the 20th century, all contain information that wasn't fully extracted at the time because the analysis tools weren't sophisticated enough. AI gives us a second chance, a way to go back and look more carefully at data we thought we'd already analysed. And every time someone does this, they find something new. The implications extend beyond just finding more objects. AI can also help with characterization. Once you've detected an object, you need to determine its orbit, estimate its size, assess whether it's active, and classify it taxonomically. All of those tasks involve pattern recognition. Does the light curve show periodic variations suggesting rotation? Does the spectrum match known asteroid types, or does it show cometary features? AI can assist with all of these analyses, processing data faster than humans, and potentially catching subtle signals that human analysts would overlook. So yes, AI is now discovering objects humans miss. And that's both exciting and terrifying. Exciting because it means we're about to learn more about the solar system than we ever have before. Terrifying because it means we've been missing things all along, and we're only now starting to realise how much we didn't see. Bernardinelli-Bernstein was sitting in archival data for 7 years. How many more are waiting? How many objects have we photographed but not recognised? And crucially, when AI starts finding them, when the discovery rate accelerates from a few per year to dozens or hundreds per year, will we have the resources to follow up on them all? Because discovering an object is only the first step. You still need to track it, calculate its orbit, and determine if it's a threat. And if AI floods us with candidates faster than we can process them, we'll have traded one problem for another. We won't be limited by detection anymore, we'll be limited by characterization. And that's a problem we need to start thinking about now, before the data deluge arrives. Part 13. The quiet upgrade to planetary defense. While Bernardinelli-Bernstein was drifting through the outer solar system, unnoticed and uncatalogued, something important was happening much closer to Earth. Planetary defense, the field of study concerned with detecting and potentially deflecting hazardous asteroids and comets, was quietly maturing from a speculative idea into a practical program. New tracking systems came online, orbital calculations improved, and in September of 2022, NASA deliberately crashed a spacecraft into an asteroid to test whether kinetic impact could alter its trajectory. The mission was called DART, the Double Asteroid Redirection Test, and it worked. The impact changed the asteroid's orbit by measurable amount, humanity proved for the first time that we could move a space rock if we needed to. The significance of that moment cannot be overstated. For decades, planetary defence existed primarily in the realm of science fiction and academic papers. People talked about what we might do if a hazardous asteroid were discovered on a collision course with Earth, but the discussions were theoretical. We had ideas, we had simulations, but we'd never actually tested whether those ideas would work in practice. DART changed that. It transformed planetary defence from speculation into demonstrated capability. We sent a spacecraft on a 10-month journey to intercept a small asteroid called Dimorphos, and we hit it. Dead centre. And the impact did exactly what the physics predicted it would do. Let's be clear about what that means and what it doesn't mean. DART targeted an asteroid about 160 metres across, roughly half the length of a football field. It wasn't a threat to Earth. It was a test target chosen because it orbits a larger asteroid, making it easier to measure the results. The spacecraft was small, about the size of a vending machine, travelling at roughly 6 kilometres per second. The impact released energy equivalent to about 3 tons of TNT, and that was enough to change the asteroid's orbital period by about 32 minutes. Not a huge change, but measurable, proof of concept. The beauty of the DART mission was its simplicity. No nuclear weapons, no complicated machinery, just a spacecraft with cameras and a guidance system, programmed to identify its target and crash into it at high speed. Kinetic impact. The oldest and most straightforward way to transfer momentum from one object to another. And it worked better than expected. The orbital period changed by 32 minutes when the pre-impact predictions suggested it might only change by about 7 minutes. The difference came from ejecta, material blasted off the surface by the impact, that flew away from the asteroid, creating additional thrust through a rocket-like effect. The asteroid got pushed not just by the spacecraft's momentum, but by its own material being expelled in the opposite direction. Now scale that up to Bernardinelli-Bernstein, 130 kilometres wide, mass measured in hundreds of trillions of tons. A kinetic impactor the size of the DART spacecraft wouldn't even scratch it. You could launch 1,000 DART missions, crash them all into Bernardinelli-Bernstein simultaneously, and the effect would be negligible. The object is simply too massive. Deflecting it would require energy on a scale that humanity doesn't currently possess. We're talking about nuclear weapons, multiple warheads, detonated deep beneath the surface to vaporize enough material that the recoil thrust alters the trajectory. And even that might not work because we don't know how the internal structure would respond to that kind of stress. The math is unforgiving. Momentum transfer scales with the mass and velocity of the impactor. DART weighed about 600 kilograms and hit Dimorphos at 6.6 kilometers per second. Total momentum transferred was around 4,000 kilogram meters per second. Dimorphos has a mass of roughly 5 billion kilograms. That's a ratio that allows a measurable change. But Bernardinelli-Bernstein, its mass is estimated at somewhere between 100 trillion and 500 trillion kilograms, depending on density assumptions. Even if you crashed 1,000 DART-sized spacecraft into it, the total momentum transfer would be a rounding error. The velocity change would be measured in millimeters per second, maybe centimeters per second at best. Not enough to matter. So you escalate, you think bigger. Nuclear weapons have been proposed for decades as the ultimate planetary defense tool, not to blow up the asteroid like in Hollywood movies, but to vaporize surface material and use the expanding gas as a propulsion system. You drill into the surface, place the warhead deep inside or just beneath the crust, and detonate. The explosion vaporizes rock and ice, creating a jet of superheated gas that shoots away from the asteroid at thousands of meters per second. And through Newton's third law, the asteroid gets pushed in the opposite direction. It's an artificial outgassing event, a controlled comet jet using nuclear energy instead of solar heating. But the engineering challenges are enormous. How do you deliver a nuclear warhead to an object travelling at tens of kilometers per second relative to Earth? How do you drill through ice that might be as hard as granite? How do you ensure the explosion happens at the right depth and angle to produce useful thrust instead of just fragmenting the object into multiple pieces that are still on a collision course? And most critically, how do you coordinate multiple warheads to fire in sequence, each one adding velocity change without interfering with the next? Because for an object the size of Bernardinelli-Bernstein, one nuclear explosion won't be enough. You'd need dozens, maybe hundreds, all precisely timed and positioned, and we've never done anything remotely like that. This is the harsh truth of planetary defence. Detection is not the same as deflection. We can find an object, we can track it, we can calculate its orbit with extraordinary precision, but if it's too large, if it's moving too fast, if we don't have enough warning time, then knowing about it doesn't save us. And that's the problem with Bernardinelli-Bernstein. It's not on a collision course, so we don't need to deflect it. But if something like it were on a collision course, if we detected a 100-kilometre comet falling toward Earth with a decade of warning time, we couldn't stop it. Not with current technology. Maybe not with any technology we could realistically develop in that time frame. The timescale mismatch is the critical factor. If you detect a hazardous asteroid 20 or 30 years before impact, you have options. Small nudges early in the trajectory can result in large changes by the time the object reaches Earth. You could use a kinetic impactor, a gravity tractor, maybe even a solar sail to slowly alter the orbit over time. But if you detect the object only 5 or 10 years before impact, those gentle methods don't have enough time to work. You're forced into more drastic measures, and if the object is massive, if it's Bernardinelli-Bernstein sized, then even drastic measures might not be enough. Gravity tractors are an interesting concept that sounds like science fiction but is actually solid physics. You park a massive spacecraft near the asteroid, close enough that the gravitational attraction between the spacecraft and the asteroid creates a tiny but persistent pull. Over months or years, that gravitational tug slowly alters the asteroid's trajectory. It's gentle, it's controllable, and it doesn't require touching the asteroid or risking fragmentation, but it's also incredibly slow. You need years or decades for the method to produce meaningful results, and the spacecraft needs to be massive, potentially hundreds of tons, just to generate enough gravitational pull to matter. For an object the size of Bernardinelli-Bernstein, a gravity tractor would be like trying to steer an aircraft carrier using a toy magnet. So what's the realistic goal of planetary defence? Not to protect against every possible threat. That's impossible. The goal is to protect against the threats we can handle. Small to medium-sized asteroids, the ones that could destroy a city or a region, but not the entire planet. Those are the objects we can deflect with existing technology, provided we detect them early enough, and the emphasis should be on detection, improving our survey capabilities so that we find these objects years or decades before they become hazardous. That's achievable. That's within reach. But defending against a Bernardinelli-Bernstein, that's a different category of problem, and we need to be honest about our limitations. The current focus on near-Earth asteroids makes sense from a risk management perspective. Objects that cross Earth's orbit are statistically more likely to impact us than objects in the outer solar system. And most near-Earth asteroids are small enough that deflection is feasible, with demonstrated or near-term technology. A 100-metre asteroid? DART proved we can handle it. A 300-metre asteroid? We'd need multiple impactors or a nuclear standby option, but it's within the realm of possibility. A 1-kilometre asteroid? That's pushing the limits, but with enough warning time, maybe 20 or 30 years, we could mount a mission. But a 100-kilometre comet? That's not a planetary defence problem. That's a species survival problem. There's a public perception gap here that needs addressing. Most people, when they hear about planetary defence programs, assume we're protected. They assume that if something dangerous were headed our way, we'd detect it and deflect it. Problem solved. And for small asteroids, that's increasingly true. But for large objects, especially large comets from the outer solar system, the reality is far less reassuring. We're not protected. We're barely surveilled. And if something Bernardinelli-Bernstein sized were on a collision course, the best we could do is calculate exactly when and where it would hit and evacuate the impact zone if there's time. That's not defence. That's triage. The word triage comes from battlefield medicine, the practice of sorting casualties by priority when resources are limited. You save who you can, you make impossible choices, and you accept that some situations are beyond your capacity to fix. That's where we are with planetary defence and large impactors. We can save ourselves from small asteroids. We're working on medium-sized ones, but large ones? The 100-kilometre monsters from the Oort Cloud? Those are beyond our current capacity. And admitting that isn't defeatism, it's realism. It's the first step toward building the capability we need. The institutional honesty matters because public trust depends on it. If space agencies oversell their capabilities, If they imply that planetary defense is a solved problem, then when a real threat emerges and we can't handle it, the backlash will be severe. Better to be upfront now. Better to say, we're working on detection, we're developing deflection technologies, but there are limits to what we can do. And those limits are real. Bernardinelli-Bernstein is a reminder of that. It's not a threat, but it's a warning label, a demonstration of what the universe can throw at us. And if we're going to take planetary defense seriously, we need to fund the surveys, develop the technologies, and plan for the scenarios we can't currently handle, because the universe doesn't care if we're ready. The next generation of planetary defense will require investments that make current programs look modest. We need space-based infrared telescopes to detect objects in the outer solar system before they get close. We need rapid response spacecraft pre-positioned in orbit, ready to launch on short notice. We need international cooperation because no single nation has the resources to handle a planetary scale threat alone. And we need a cultural shift, a recognition that planetary defense isn't a luxury or a science project, it's infrastructure. It's as essential as weather satellites and earthquake monitoring. Because the impact that ends civilization won't announce itself decades in advance. It might give us years, it might give us months, and if we're not ready, if we haven't built the tools and systems and international frameworks to respond, then all our knowledge and all our technology won't matter. Bernardinelli-Bernstein is teaching us that lesson now, while we still have time to learn it. Part 14. The New Physics of Ice. Let's talk about ice, because when most people hear the word, they think of frozen water, the stuff in your freezer, the kind that melts when you leave it on the counter. But in space, ice is not soft, it's not fragile, and depending on the temperature and pressure, it can behave more like rock than anything you'd recognise as frozen water. This is the new physics of ice, and it's critical to understanding how objects like Bernardinelli-Bernstein hold together and evolve over billions of years. Water ice, the kind we're familiar with, exists in multiple phases. The ice cubes in your drink are ice IH, the normal crystalline form that occurs at everyday temperatures and pressures. But if you squeeze ice hard enough, increase the pressure dramatically, the molecules rearrange into denser structures. Ice 2, Ice 3, Ice V, Ice Vs. These are exotic high-pressure phases of water ice that don't exist naturally on Earth's surface, but are common in the interiors of large icy moons and comets. And some of these phases are harder than granite. The pressure thresholds for these transformations are extreme by terrestrial standards, but routine in large cosmic bodies. Ice 2 forms at pressures around 2,000 atmospheres, roughly twice the pressure at the bottom of the Mariana Trench. Ice thick requires pressures exceeding 10,000 atmospheres, and at those pressures, the molecular structure of water becomes unrecognizable. The hydrogen bonds twist into configurations that create crystalline lattices denser than any ice you've ever touched. Some of these high-pressure ices don't even melt when heated. They transform directly into other ice phases, creating a complex phase diagram that looks more like a roadmap of chemical possibilities than anything simple. Bernardinelli-Bernstein's interior likely contains high-pressure ice phases because the object is massive enough that its own gravity compresses the core. The outer layers are probably ice I, normal water ice mixed with other volatiles like carbon monoxide and methane. But deeper down, the pressure increases, the ice transforms, and at the very centre, if the object is differentiated, there might be a rocky core surrounded by layers of increasingly exotic ices. The exact structure depends on the thermal history, the composition, and how much the object has been processed by collisions and outgassing. But the key point is this: the interior is not a uniform snowball. It's stratified, layered, complex. Think of it like an onion, except each layer has different physical properties, different density, different thermal conductivity, different mechanical strength, and those differences create boundaries, interfaces where one type of ice meets another. Those interfaces matter because they can trap heat, redirect pressure, and create zones of instability. When you have a comet nucleus the size of a city or a mountain range, these internal structures become mechanically significant. They determine how the object responds to stress, how it fractures, how it holds itself together against the forces trying to tear it apart. This matters because it affects how the object responds to heating. When sunlight warms the surface, the heat doesn't penetrate uniformly. It conducts through the ice, but the rate of conduction depends on the phase and the temperature. Some ice phases are better thermal insulators than others. and if there are layers with different thermal properties, you can get situations where heat gets trapped at certain depths, creating pockets of warm ice surrounded by cold ice. Those pockets can build pressure, they can expand, and if they crack through to the surface, they create jets, outbursts, localized areas of intense outgassing that don't match the smooth models we use for small comets. The thermal conductivity variations are dramatic. Ice conducts heat relatively well, though still far less efficiently than rock. But some high-pressure ice phases act as thermal barriers, slowing heat transfer to a crawl, and if you have a layer of insulating ice sandwiched between more conductive layers, you create what engineers call a thermal trap. The heat accumulates, the temperature rises locally, and the ice at that depth starts to behave differently, perhaps softening, perhaps sublimating if there are volatile components mixed in. The result is unpredictable internal dynamics, pressure building in regions you can't observe from the outside, waiting for a structural weakness to provide an outlet. Volatile trapping is another complication. When a comet forms, it incorporates ices of many different compounds: water ice, carbon monoxide ice, methane ice, ammonia ice. Each of these has a different sublimation temperature. Carbon monoxide sublimates at very low temperatures, around 25 degrees Kelvin. Water ice doesn't sublimate significantly until you reach temperatures above 200 degrees Kelvin. So as the comet approaches the Sun, the super-volatile ices sublimate first, leaving behind a matrix of water ice and rock. But if that sublimation happens deep below the surface, the gas has to percolate up through overlying layers, and if those layers are dense and compacted, the gas can get trapped. The permeability of ice is another variable nobody talks about enough. Fresh porous ice lets gas escape relatively easily, but ice that's been compacted by pressure or sintered by repeated thermal cycles becomes impermeable, a solid barrier that gas cannot easily penetrate. And when you have meters or kilometers of impermeable ice overlying a layer where volatile ices are actively sublimating, the gas pressure builds. It's not immediate. It's not explosive at first. It's a slow accumulation, molecules escaping from ice crystals and collecting in microscopic voids, those voids expanding and connecting, forming channels and pockets, until the pressure reaches a critical threshold. Trapped volatiles are dangerous because they build pressure. Imagine a sealed bottle of soda. Shake it up. The carbon dioxide gas wants to escape, but the bottle holds it in. Open the cap and the gas explosively decompresses. The same thing can happen in comets. If a layer of high-pressure ice traps carbon monoxide or methane below it, and then the overlying ice weakens or cracks, the trapped gas bursts out. You get a sudden outburst, far more intense than the steady background outgassing. And if the object is as large as Bernardinelli-Bernstein, those outbursts can be spectacular. The scale of a potential outburst scales with the volume of trapped gas and the strength of the confining layers. For small comets, an outburst might create a jet visible for a few hours or days, ejecting dust and gas at speeds of hundreds of meters per second. But for an object 130 kilometers wide, with potentially cubic kilometers of trapped volatiles building pressure over millions of years, an outburst could be catastrophic. Not catastrophic in the sense of destroying the comet, its gravity is too strong for that, but catastrophic in the sense of fundamentally altering its surface, opening new vents, exposing fresh ice, and creating visible changes in brightness and activity that would be detectable from Earth even at extreme distances. Surface evolution is the final piece of the puzzle. Comets that make multiple passes through the inner solar system develop thick crusts. The surface ices sublimate away, leaving behind a layer of dust and non-volatile material that insulates the interior. That's why old comets become less active over time. But Bernardinelli-Bernstein is pristine. It's never been this close to the Sun before. Its surface hasn't been processed. And that means the outgassing patterns we observe now might change dramatically as the object continues to approach perihelion. The surface might crack, new vents might open, old vents might seal over. We're watching a surface evolve in real time, and we don't have a good model for what that looks like at this scale. Surface texture matters more than you'd think. A smooth surface radiates heat evenly. A rough surface with craters and ridges and cliffs creates shadows and hotspots. The shadows stay cold. The sunlit slopes heat up, and that differential heating creates thermal stress, the same stress that causes rocks to crack in a desert when the temperature swings from freezing at night to scorching during the day. Except on Bernardinelli-Bernstein, the temperature swings are happening over decades or centuries as the object slowly approaches the Sun. The ice expands, the ice contracts, fractures propagate, and eventually something gives. The colour of the surface also influences how much heat gets absorbed. Dark surfaces absorb more sunlight than bright surfaces, and comets are generally dark, covered in organic tars and carbon-rich compounds created by radiation processing over billions of years. But if an outburst exposes fresh ice, suddenly you have a bright patch on an otherwise dark surface. That patch reflects more sunlight. It stays cooler. And the thermal evolution of that region diverges from the rest of the surface. You get localized differences in activity, some areas outgassing heavily, while others remain dormant, creating an asymmetric distribution of jets that complicates orbit calculations, because the outgassing exerts a small but measurable thrust on the nucleus. All of this matters for astrobiology, believe it or not. Because if large icy bodies like Bernardinelli-Bernstein contain pockets of liquid water in their interiors, trapped between layers of high-pressure ice and heated by radioactive decay or tidal forces, then those pockets could potentially support microbial life. We know that life can exist in extreme environments on Earth, deep underground, in subglacial lakes, in hydrothermal vents, and if similar environments exist inside icy bodies in the outer solar system, then those objects are potential habitats. Not likely, not proven, but possible. And that changes how we think about astrobiology. It's not just about Mars or Europa or Enceladus. It's about every large icy body in the solar system, including the ones we haven't detected yet. The requirements for life as we know it are surprisingly minimal. Liquid water, an energy source, organic molecules, and time. Bernardinelli-Bernstein has been drifting through space for billions of years, long enough for radioactive elements like uranium and thorium in its rocky core to generate heat through decay. That heat conducts outward slowly, warming the overlying ice, and if the pressure and temperature conditions are right, if there's a sweet spot somewhere between the frigid surface and the warm core, liquid water could exist, not a vast ocean. More like isolated pockets, maybe only meters or kilometers across, insulated by surrounding ice, persisting for millions of years. Whether life could originate in such an environment is an open question. Life on Earth probably started in a much more dynamic setting, with energy inputs from sunlight or hydrothermal activity, and access to a wide variety of chemical compounds. But once life exists, once it evolves the ability to extract energy from chemical gradients or radioactive decay, it can colonize environments that seem impossibly harsh. And if panspermia is real, if microbial life can survive ejection from one planetary body and arrival on another, then objects like Bernardinelli-Bernstein could be carriers. Frozen arcs drifting through the solar system, their interiors potentially hosting microbial passengers that have been dormant for eons, waiting for conditions to improve. The implications extend beyond our solar system. Every star likely has an Oort Cloud equivalent. Every planetary system probably ejected massive icy bodies during its formation. And those bodies are drifting through interstellar space right now, dark and invisible, potentially harbouring frozen ecosystems in their interiors. If life can exist inside a comet nucleus, then the galaxy might be full of life in the most unexpected places. Not on planets, not in oceans under the ice of moons, but inside the comets themselves, insulated from radiation, protected from cosmic rays, drifting through the void until they fall back toward a star and briefly thaw before returning to the frozen darkness. Bernardinelli-Bernstein might just be ice and rock, but it might also be a reminder that life finds a way, even in the coldest, most unlikely corners of the universe. Part 15. The real takeaway. So what have we learned? What's the thesis that ties all of this together? Because Bernardinelli-Bernstein is not just a curiosity, not just a record-breaking comet that astronomers will study and then file away. It's a warning label, a reminder that the universe operates on scales and timelines we struggle to comprehend, and that our understanding of the solar system is still incomplete. We thought we knew what comets looked like. We thought we knew how big they could get. We thought we knew where they came from and how they behaved. And then Bernardinelli-Bernstein appeared in archival data, and everything we thought we knew had to be revised. Expectations versus predictions. That's the distinction we need to internalize. Expectations are what we assume will happen based on existing models. Predictions are what we calculate will happen based on specific data. Expectations told us that Oort Cloud objects should be small, a few kilometers across, dark and unremarkable. Predictions, once we had enough data on Bernardinelli-Bernstein, told us it was 130 kilometres wide and outgassing at distances where comets shouldn't be active. The expectations were wrong. The predictions so far have been accurate, and that's the lesson. Trust the data over the models, especially when the data shows you something you didn't expect. Order is an illusion. We like to categorise things. Comets go here, asteroids go there, planets are this, dwarf planets are that. But the universe doesn't care about our taxonomy. It produces every possible variation, every transitional form, every edge case that breaks the definitions. Bernardinelli-Bernstein is a comet that behaves like a dwarf planet. It's a dwarf planet that outgasses like a comet. It's neither and both, and trying to force it into a single category misses the point. The categories are tools for organising information, but they're not the reality. The reality is a continuous spectrum of objects with different sizes, compositions, orbits and histories, and the sooner we accept that, the better we'll understand the solar system. Slow threats versus flashy ones. This is the bias that Bernardinelli-Bernstein exposes. We're obsessed with fast-moving asteroids because they feel immediate. They cross Earth's orbit. They have short warning times. They demand attention. But slow-moving giants from the outer solar system are just as dangerous, potentially more so, and they get far less scrutiny. Because they're far away. Because they move slowly. Because we assume we'll see them coming. Except we didn't see Bernardinelli-Bernstein coming. We found it in old data. And if there are more objects like it, if the Oort Cloud contains dozens or hundreds of massive bodies that haven't been detected yet, then our threat assessment is incomplete. Misfiled objects as existential risk. This is the scariest takeaway. Bernardinelli-Bernstein was sitting in the Dark Energy Survey database for years, classified as a trans-Neptunian object, a minor planet, something unremarkable. It took careful analysis by experts to realise what it actually was, and that makes you wonder, how many other objects are misfiled? How many comets are catalogued as asteroids because they haven't outgassed yet? How many large objects are classified as small because their albedos were estimated incorrectly? How many distant threats are hidden in plain sight, waiting for someone to look closer? Scientific humility is not weakness, it's honesty. When astronomers say, "we don't know," when they publish papers with large uncertainties, when they emphasise that their models are approximations, that's not a failure. That's integrity. Because the universe is complex and our observations are limited, and our theories are incomplete. And admitting that, acknowledging the gaps in our knowledge, is the first step toward filling those gaps. Bernardinelli-Bernstein has taught us humility. It's shown us that we can't assume the outer solar system is empty or harmless. We can't assume our surveys have found everything worth finding. We can't assume that the largest comet ever detected will remain the largest forever. Future discovery inevitability. This is the hopeful part. We're going to find more better telescopes, more sensitive detectors, smarter algorithms, the Vera Rubin Observatory, the James Webb Space Telescope, AI-powered data analysis. All of these tools will reveal objects we've never seen before, and some of those objects will be larger than Bernardinelli-Bernstein. Some will be stranger, some will challenge our understanding even more profoundly, and that's exciting, because every new discovery is an opportunity to learn, to refine our models, to update our understanding of how the solar system works. The cost of assumptions. This is the pragmatic takeaway. Assumptions kill. Not literally, not usually, but they create blind spots. They make us overconfident. They let us ignore data that doesn't fit. And in planetary defence, in astronomy, in any field where accuracy matters, assumptions are the enemy. Bernardinelli-Bernstein was almost missed because astronomers assumed it was something ordinary. And if the next Bernardinelli-Bernstein is on a more dangerous orbit, if it's falling toward the inner solar system with a shorter warning time, we can't afford to make the same mistake twice. We need to question our assumptions. We need to verify our classifications. We need to treat every slow-moving object as potentially significant until proven otherwise. And here's the final thought, the one that should stay with you after the video ends. The universe doesn't hide. It's not secretive. It's not malicious. Every object in the solar system is out there, orbiting according to the laws of physics, reflecting sunlight, moving through space. The information is available. The data exists. But we have to look. We have to analyse. We have to interpret. And sometimes the most dangerous objects are the ones we've already seen but didn't recognise. Bernardinelli-Bernstein was there all along, glowing faintly in archived images, waiting for someone to realise what it was. The universe doesn't hide, our categories do. And if we want to survive in a cosmos full of massive frozen worlds and slow-moving threats, we need to see past the labels and look at what's actually there. Because the next Bernardinelli-Bernstein might already be in the data, it might already be falling, and we won't know until someone takes the time to look.